Hey, welcome back. So in the last one, we just graphed a square root function that only had a multiplier, which affects our how skinny or how wide our arc is. Now with our next one, we are going to talk about how when we have a +2 or like outside of the square root, if we have a number that we are adding or subtracting from our square root, how that affects our how that affects our graph. And so the numbers I'm choosing for the table are going to be so that we can compare these to the parent function in the first video. And so the parent function used x values 0, 1, 2, and then it skipped to 4 and 9. Now, if I'm going to be completely honest with you, especially looking at the one we have right here where it's the square root of x and nothing else, I'm picking x values that are going to be perfect squares because then I don't have decimals to deal with. So if you pick perfect squares, you're going to have whole numbers. But again, I'm wanting to show you how this function compares to that parent function. So I'm going to plug these values in for x. So we're going to have the square root of 0 plus 2, which is 2, the square root of 1 plus 2, which is 1 plus 2, which is 3. Square root of 2 is not a whole number. That gives us a decimal. And then that decimal plus 2 gives me, so when I plug in 2, square root of 2 plus 2 is approximately 3.4. When we plug in 4, square root of 4 plus 2, we'd end up with 2 plus 2, which is 4. Square root of 9 plus 2, square root of 9 is 3, 3 plus 2 is 5. And so that's our table, and our next step is to then graph. Again, because we have these decimals, I'm counting by half points, so this is my y values by half points. So we have 1, 2, 3, 4, and 5. And then I'm going to count by 2s down below. 2, well, by 2s. I'm counting by 1s, but writing the 2s. 2, 4, 6, 8, 10, 12. Okay. So from here, we're just going to graph. We have the point at 0, 2. That's our first point. 1, 3, 2, 3.4, so just beneath. And then we're at 4, 4, and 9, 5. And then from there, we draw our arch, right? Our little half parabola on its side. Now, I want to show you, this was our parent function graph. Right here, we had the points 0, 0, 1, 1, 2, 1.4, 4 was at 2, and 9 was at 3. So if you notice, looking at our tables, each of these we added 2 to the parent graph to get our new position. So when we have that plus 2, or even if it was a -2, then we would subtract from all of them and we would go down. But our parent function, if I were to graph that parent function, it would be coming in looking like this. And so it is just pretty similar, just lower by 2 points. And so there is our, that was terrible, but this is that y equals the square root of x. And then this is our y equals the square root of x plus 2. So just so you can see the difference in those shapes. All right, So on our next one, we have now put it inside the radicand. Okay. Now again, if I were creating these in order to make it easy to graph, inside my radical, I would be mentally figuring out what do I do, what x would get me to perfect squares so that I would have whole numbers. But again, our purpose for this video is to show you how it compares with that parent function we already know. Now, because I know what's going to happen here, we're actually going to move our, and I'm going to try my best to draw it. It's probably not going to look very good. We're going to move our y-axis as I snake it down there, our y-axis to right here. The reason being is because I goofed and didn't get at least quadrant 1 and quadrant 2. Again, I know what's going to happen. I'm going to choose those same x values so that we can compare it. Actually, I'm going to choose, I want my y, my first y, to be 0. And so in order for that to happen, inside my square root has to be 0. So I'm going to first figure out what my what does my domain have to be in order for this to be true. And so again, x plus or plus 3 has to be greater than or equal to 0. So that means x has to be greater than or equal to -3, meaning my bound is -3. So I'm going to start at -3, go -2, plug in 0. I think I went 1, 4, and 6. Why? I'm not sure. Yes, am I doing way more numbers than has to be done? I am, but we're going with it. It's probably what the book told me to do. But remember, x values are ones you choose. I want this -3, that bound, because that's where we're crossing the x-axis. That's a must, because I need where that y is 0. After that, it's whatever I want it to be. So here I'm going to do the square root of -2 plus 3, so I'd have the square root of 1, which is 1. I'm going to do the square root of 0 plus 3, which is approximately, this one is a little too big. So when x is 0, my square root is 0, or is square root of 3, which is approximately 1.7. We plug in 1. 1 plus 3 is 4. Square root of 4 is 2. Plug in 4. We have 4 plus 3 is 7. Square root of 7 is approximately 2.6. Plug in. Now, I know why I chose 6. I chose 6 because the square root of 6 plus 3 is 9, and the square root of 9 is 3, and it gives me that whole number. So if we're being truthful here, I would have, my own table, I would have chosen -3, -2, 1, and 6. Those would have been the numbers I chose because I would get that perfect square underneath the radicand in order to get a whole number answer, because I really dislike graphing decimals. And then from there we graph. So this is going to be my -3, -1, 1, 3, 5, 7, right? And then again, just like we were doing before, I'm counting these up. Every 2 is a whole number. So at -3 we are at 0. So we're -3, 0. And then -2, we are at a +1. And of course that keeps, love it. I'm going to go ahead, you know how to graph points, so I'm going to pause and they'll magically appear. All right, and so I went ahead and graphed it. I went ahead and graphed the parent function. So this bottom one, there we go. This bottom one is y equals the square root of x, whereas this top one is y equals the square root of x plus 3. Notice that when it's on the inside, it shifts us left to right. And it is opposite to the sign inside the square root. So we have a plus 3 inside the square root, but we shifted left 3. If we had a minus 3 inside the square root, we would shift right 3. But other than that, our numbers would be the same. If I would have plugged in -1, my -1 for x would have given me the 1.4 that I get when I plug in 2 on my normal, on my parent function. So it's all about how our numbers shift to get us so that we can figure out our graph. If you can figure out how they shift, then you can just mess with the table of the parent function instead of having to recalculate it every time. So just an idea. Also, if you know how it shifts, then you can look at your graphs if it's a multi-choice question and say, oh, well, based off of the fact that this has the plus 3 on the inside, I know that I'm going to shift definitely my 0, 0 point from my parent function left 3. So again, just some things to keep in mind. If it's inside, we call that h, and then the outside's k. So we have the square root of x opposite h plus k. That's our basic function. Y equals that. This opposite h, that's our horizontal move. And again, if it's positive, we're moving left, is a left move, and negative is a right move. And then, so that's our h. K is vertical. I'm trying to find, there we go. K is a vertical move. Positive is up, negative is down. And so that's how, knowing what we know, you could mix them together and make an entire move. I believe in the homework, it's just one or the other. But now you have your cheat code there to make it just a little bit easier. And again, if you understand the cheat code, then you can manipulate the parent function table that was given to you in the first video. So if you have any questions, reach out and we'll see you around.